Okay.
So the thing is stuck for him, you know, that cat.
That's sad.
Okay, he's trying to get in.
Let me get into.
What prompted the
What?
the question?
About?
First things first.
Statement.
Your placement percentage, and people knowing things when they go out into the real world.
Well, I mean, we said we're gonna lecture and you don't see people, so it's certain individuals.
No.
So,
Am I invisible again?
certain individuals. I'm not saying everybody. I'm saying
Well, Chad is well aware that you're here, Chad.
I wore my brightest sweater so that he wouldn't miss me. Damn it, he said.
okay. Somebody help me here with the transformer sizes. Was it seven something? Okay, let's go, guys, to 7, 7, 6, and 7, 7. You guys go and DeWalt to 7, 6, and 7, 7. And here's my example. I want to have, oops, let's turn the light off. I want to have an example, guys, transformer. Question number 1, transformer. I have this transformer, believe it or not. I do have a delta transformer. I have a delta transformer, guys, and this transformer has a big, pick a big boy for this transformer. This transformer is 1, 2, 3, 10 meg. Let's do a 10 meg. 10 meg kVA. 10 mega kVA. And the voltage on this side, the voltage on this side, let's continue with 13.8 kV, and in this side 4160 volt. So it's two sides, primary, secondary, higher voltage. Okay, primary, secondary, higher voltage, primary and secondary higher voltage. I want to bring to your attention, guys, Mother Earth again. And we're going to do, let's start with the primary. With the primary, we always, let's do the conductor, number 1. The overcurrent protection device, number 2. Number 3. Number 3, let's make the conductor again, number 3, and the overcurrent protection device, number 4. And number 5 is the grounding electrode conductor, the grounding electrode conductor. Ground. This is phase A, phase B, and phase C. Phase A, phase B, phase C. So we have a medium voltage transformer, guys. Let me just grab some copy here. So I can have my engine running here. Thank you, Mr. Medium voltage transformer. Let's put the impedance for this transformer. Add an impedance for this transformer. The impedance of this transformer, guys, is 6%. This 6% is impedance of the transformer, 6%. I need to find all this stuff.
Is that 10 M? I'm sorry, Chad, is that 10?
10 MkV.
10 M.
Yeah, mega. million. Big boy. That's what you guys see at this voltages, 10 meg. So instead of 10,000 kVA, 10,000 kVA, that will get you 10 mega kVA. I'm sorry, 10, why did I say K? 10K, there's no K here. Thank you. 10K. 10 MVA, which is 10,000 kVA. Okay. If you guys do me a favor, just to satisfy, I'm going to have the short circuit calculation too in a second, but let's go to Article 450 and do the sizing. And yesterday I told you which table we're going to go to size the. So, since Mr. Erbab, if you look, primary and secondary are higher than 600 voltage, then we're going to go to B. All right, let's go size the conductors. Number one, I want to say primary feeder. For the primary feeder, guys, if you remember how we do that, look at that, medium voltage, nothing changes. So I have I primary equal, what's the 10 meg? 10, I'm just going to bring to your attention, 10 meg is actually 10, 0, 0, 0, 0, 0, 0. Don't forget that 10 meg is 10 million. Divided by 1.73 times 13.8 is 13.800, right? This is 13,800. I don't put the zeros, guys, most of the time, but I put it here because it's a 10 meg and we don't use 10 meg. I've not used them in example before. I don't have an example already done for you, so I need somebody to do the calculation, help me with it. 419. Thank you. 419 M. 419 M. 419 M. 419 M. Any question, guys, about that? 419 M. Continue with the tradition of continuous load, which really doesn't make a whole lot of sense in medium voltage, but let's continue the tradition. 1.25 times 419 red 419 5.4
524.
520 224 524. Okay. And Mr. Erbab, we said yesterday we're going to grab this gentleman amp wise. We're going to grab it, go to 310.69. Is that what we did? 79 table. Under which column? You can either go to 105 or 90, unless you know, go 90 always. So 90 degree Celsius. And I know I need 3 of them. Everybody knows why 3 of them? What happened to the neutral, Chad? I don't need a neutral. There is no neutral. They're delta. 3 conductors. Number 750. Thank you. Under. Did you look at 13.8? So it should be on the other side of the. Because there are 2 sides. 750. The one. You'll have to go to the other side because it's the voltages. Because I know that's a common mistake.
Still 750.
Still 750, okay. But you guys see it, because the voltage is 13.8, you're going to go to the right side of the table. The right side of the table. Everybody's with me? The right side of the table. It's still 750 kcm. So 750 kcm. 3 conductors, 750 kcm. Any question, guys? Straightforward. They're coming multi-conductor. We're assuming it's a multi-conductor cable here. We're assuming it's a multi-conductor cable based on multi-conductor cable. I want.
Is this outside?
Underground ducts. What do you mean?
Do we have to, well, then do we have to derate
For
the temperature of the conductor?
it's underground temperature. These table. Look at the table. It give you
Mm,
ground
the
temperature.
table.
It's based on the ground temperature.
Oh, okay.
Yeah. They're underground ducts. They give you 20, I think 20 Celsius. Is that what they give?
Yeah,
20 Celsius ground temperature.
because you choose the table based on how it's.
Based on the ground temperature and based on the loading and a bunch of factors there. 750 kcm. One multi-conductor cable. Now Ryan might check for us at one time if Southwire make them. We might have to move to a different format just because they don't make a multi. That's a big conductor, 3 conductors in one big cable, 750 each. I don't know if they make them. What do you do if they don't? Then you go to a different table that allow you, or different configuration that allows you. Let me just go look at it. That allows you to run one cable per duct, and or or single conductor cable. So let me just go quick here, guys, and see if we might have an issue here. The conductor is too big. Let's look at you guys at 79, right? 79, 70, 79. Okay, let's look at detail. So this is detail 1 is one conductor cable, 3 circuits. These are for 3 circuits, 6 circuits. Detail 1 circuit, 1 circuit. Detail 1 circuit.
So
We
it's 3.
So it's still the same calculation, guys. It's 1 circuit. It could be a multi-conductor, but the conductor is consisting of 3 insulated cover conductors cabled within an overall covering. So it's a multi-conductor cable, 3 conductor cable in underground ducts, 1 cable per electrical duct based on ambient. So it is a cable here. 3 insulated aluminum cable with 3 conductor cables. So you might have to go single insulated aluminum. 81. It says, and basically of single insulated copper conductor directly buried in earth based on ambient temperature. That could work for us. Or 3 insulated conductor cable, multi-conductor cable, triplex. Let's just stay with it. But these are what you're going to be looking at. How am I going to be doing my format? Let's assume, guys, most of the time, you rarely end up with a big cable like this one, and this in the utility side. So let's assume the detail number 1 will work for us. But these are questions you're going to be asking yourself. Will it work or not yourself? Detail 2, 3 circuits, 3 circuit C-fig. Detail 2, 3 circuits nodes, not 3 conductors. 3 circuits. You still have. This is just for 3 circuits. Each circuit has 3 phases. 3 circuits. You're still using a multi-conductor cable. You need to look at a cable that can give you a single conductor cable configuration. And the only one that's single is the 81 give you a single insulated copper conductor direct buried though. If we want to put in a duct, we have to go single insulated aluminum triplex. The one before, I think, before the ambassador of 3 single. Okay, how about ambassador of 3 single insulated copper conductor in underground ducts, 3 conductor pure electrical duct here. 77. Can you guys look at 77? Ambassador of 3 single insulated copper conductors in underground electrical ducts, 3 conductors pure electrical duct. That's what you want. 3 conductors based on ambient. So if you guys look at this, might be the best scenario for us. Detail number 1. Okay. You guys might, just because of the size, I'm going to really change the table. Because that you might not be able to get that size. So I'm going to 310.77. Table 310.7. But everybody knows why I changed it, guys? 78, not 79, 77. Everybody knows why I changed it? That's 77. You might not get a multi-conductor cable 700 kcm, but definitely you will get a single conductor cable 750. So 3 single conductor 750. Perfect. Still the same size?
Yeah.
Yep, same size.
But just the difference is it's 3
The
conductors.
yeah,
instead
3
of
conductor.
one.
Everybody knows these are 3 conductors,
And there are
3 single conductor cables. 3 conductors in one duct.
In a single block?
In a single duct. Yep,
Yeah.
that's detail 1. Is that what you guys looked at, detail
Yeah.
one?
I don't understand those details. That to me looks like one cable and one box.
Just understand.
Yeah, they're confusing. Let me just, guys, the cables, like, let me just go back one here. Let's look at detail one. Detail number one. Detail one is giving you this and giving you that little thing inside it. Okay? If you use detail one with table, that's where the confusion is. If you use this one with table 310.79, this means 3 conductor cable. And if you use it under 310.79, if you use the same detail under table
What's 77 is the
310.77, that's the single conductors.
Yeah, 77.
Yeah. So if you use it under this table, the same detail, that thing means three conductors. Done. 3 conductors. Yeah. But I know where you see.
The details, I understand.
Yeah, the detail.
Well, I can read the table and understand what I'm getting.
But it's misleading.
The details.
They should have one detail which shows 3 and one detail which shows 1. Really. Ryan, my friend?
Those are actually not convolutional.
A dot. Yeah. But that dot's supposed to be a cable or a.
No, I understand what the dot.
The
Yeah.
duct I get, it's just, if we're gonna
Brad,
run 3 cables.
I want you,
put 3
both of you, Brad and Ryan, I want you guys to look at the bottom of the table 310.60. Way at the bottom it says that dot is identified as cable or cables. Can you guys see that?
I understand.
Yeah.
He was asking if it's a conduit. Just a
It
conduit.
shows as dot. In the legend, yes, it says electrical dot. It's funny that they don't put that as a square. Because that's what it would be.
Square dot? No, these will be PVC conduits or
Or we just put details inside of detail 1.
yeah. But do you see guys that black dot is identified as a cable or cables? Could be one cable, multi-conductor cable or cables. But no, these are round dots. I've never seen other than circular dots. And they can be PVC, could be 6-inch PVC, or you can make them. They can make them from concrete dots. You can pull them in concrete dots, or the most common ones is PVC. You with PVC schedule 80 and do the formation of them.
Okay, not to just belittle the point, but if it's PVC underground, what's the difference? It's just a wording issue, right?
If it's PVC underground, because a duct could be a PVC, could be
I mean,
yeah.
conduit or duct.
Yeah.
Really,
It could be
one and the same.
yeah, it could yes, it could be the same, but like we don't have a concrete duct in the NEC code book, do we? If you go look at the NEC code book, you can't buy a 3-inch concrete conduit, can you? Though as a duct, you can design a 6-inch fiber. What do you call them? Fiber. There's the help me here with the terminology. They have fiber optics, fiber conduits, and different materials. They use different materials, guys, to make ducts. Conduits are mainly either EMT or PVC, but they can use different materials to make the ducts. That's kind of my
It's
shot.
like a duct bank. So that's like a
Yeah,
concrete.
but that duct bank could be conduits PVC or could be conduits other than PVC.
I've never worked with any.
Okay.
I get it. I'm fine.
Good. All right. Good.
I figured it out from the table.
But we need your answers though.
The IP here, primary computers, IP equals 10 million.
Yep.
By 1.73.
Yes, Mr. Bell.
Is that that's 138000.
This one,
Yeah.
this is 13,800, Mr. Bell. If you put 13.8K, right? It's
1.8, yeah, okay.
now million here. This is a K.
Okay. Yeah, 138. The 13.8, right?
Yep,
Yeah, you're right.
that's where it came
Yeah,
from.
yeah, I got you the point.
All right, so coming here, guys. So let's go do two. let's keep this detail here. And I'm gonna do number two. What did we say number two? Number two is overcurrent protection device. Primary overcurrent protection device. Primary overcurrent protection device. What was the size first? What was the size that we came up with? 419. So I have 419. And Ryan, what's the multiplier from the table? Anybody can give me the multiplier from table 450.3b.
You're in a circuit breaker?
Fuse. We're using a fuse.
300.
Fuse. 300? 300. So that will get you 1200 something. Anybody has a calculator?
1257.
How much?
1257.
1257. Does it have a note number 1 on it?
Yes.
Okay, so what does that mean? Go
Go
up?
up.
So all this is coming guys from 450.3b or A. Is it A or B? 350 dot, we got A. We got carried from A. Okay, so you're gonna go up. Where do you go up and down though? You need to go to where? Our 240.6, our all-time 240.6 boy. And that'll get me 1500. 1600, you don't have 15. 1600 M. Gentlemen, here's the fuse that you're looking at. So basically you're looking at, no, this is not 1600, but that's the size of the fuse. This is actually 65 amps.
What's that go to?
To 65 amps. Fuse.
Still at hot.
This is 13.8. You bring the hot. This is where you go put it right in here.
Oh, cool.
Expulsion proof, rated. The reason why I brought this one with me, guys, it's rated for this guy. If you read it, it's rated for 15.5 kVA. Would that be cool if it's rated 15.5 kVA? Would it be good at 13.8? No problem. And the amps on it is 65 amps. It doesn't work on this. We need a bigger amp than that. The interrupting rating for it is 50 kiloamp. 50,000 amps can interrupt 50,000 amp at 15.5 kVA. A huge amount of energy out of this boy. Okay, so we got our primary. Any question, guys, about the primary fuse? I picked a very big, large transformer, guys, so that's why the numbers are big. Number three, secondary feeder. And Mr. Erbab, you take your 10 meg, divide this by 1.73 times 44160. Don't forget that these are 10 million. Anybody come up with a number? It's gonna be a big number. 13. 1390. 90M. Thank you. Ryan, 1390M. Okay. Let's go size the conductor now. Now, when we size the conductors, let's see which detail we want to go to based on how many circuits. Because we're going to parallel here. We're going to be paralleling, guys. So let's see which detail should we go to based on paralleling. All right, let me click here. Continue with, I'm going to take 1.25 times, what was it again? 1390. 1390. Any idea? 1738 amp. Okay. Now where am I going to go? Which detail? 1738 Okay, 17, like say 1738, so 1700 amps. If I divide by 18, I need to fit it, divide this by 6. Let's try to use detail number 3. Divide this by 6, guys. Detail number 3. Can we get it to fit with detail number 3? Detail 3, 6 circuits. I'm gonna tell you why I did that one. I'm gonna take the 1738 amps, divide this by 6. Why did I divide by 6? If you guys look at detail number 3, it will give you 6 circuits in one duct. And here's detail number 3. You look at detail, this is where I'm looking. That's how I'm gonna pull my system based on this detail. 6 circuits, multi-conductor. Oh boy, but these are multi-conductor circuits. Can we find, multi-conductor cable? What's the amp, how much amp do you get here? I'm just gonna see.
290.
Oh, so we might be able to. 290. Yeah, we can probably, the size for this size, we might be able to. Okay, so let's take the 290, take this one to table 310.70, not the 9. We're gonna use a 79.
2000. It's less than 2000.
Yeah, 3 single conductor cable. Yeah, 79. 379. You're right, Mr. Bab. 79. Under detail. Which detail? Number 3. So these are multi-conductor cable, 3 duct multi-conductor cable. What size do you get, Brooks? 500. We're close. So this is going to be 500 kcm cable. And how many of these? So this is how I write it. 3 conductors, 500 kcm cable, one cable, multi-conductor. Okay, and how many of them do I have? I have 6 sets. Okay, so if you guys look at the detail that they have, here's the detail. This is how it's gonna look like. 1, 2, 3, 4, 5, 6, and to make Brad happy, we're gonna make this is a dot. We're gonna make here's a conductor, and another conductor, and a conductor, and red. Here's the phases, all the 3 phases. And you know what they did with them, guys? I don't have another color, so I'm going to put a cable. And then they cabled them. All these are cabled together. Does that make sense? They're one cable, multi-conductor cable. So that's detail number 3. Multi-conductor cable we pulled, then we carry this set. 6 sets. Huh? Don't use it. At least we found something that you haven't done, Mr. View. For Pete's sake.
Well, the duct bank, like you're using high voltage now.
Yeah.
You're using 13
Yeah.
You know, that duct bank that I've had to install, and this is usually what's done is you have rigid conduits encased
In concrete.
red concrete. That's the guide, because that way if anything hits it and they see that it's red, it's a warning sign. And then tracer wires and also a single conductor or multi-conductor cable and a single pipe encased in concrete. I haven't seen much. None of the same stuff. None of the stuff is like that.
I assure you they're there. Now, what type of conduit? That's a whole different story. PVC or fiber conduits or concrete conduits, that's a different, or duct, that's a different story. But okay, so we got that one. The second one, my friends, we're gonna do is Mr. Erbab, number 4, secondary overcurrent protection device, and I'm a fuse guy. By the way, when you go to the medium voltage, Holly, fuses are your overcurrent protection device of choice. Circuit breakers are very expensive on medium voltage. We use them, but they're very expensive. So your fuses becomes your overcurrent protection device of choice. Okay, so what did we say the amps on them? Can you just give me the amps again that we found? 1390. So you take the 1390 multiply by, I think 3 again, from table, which table? 450.38. It's a fuse. Look at the 250. Okay, for a fuse, 250.
Yes.
Do they have the note number 1 on it?
Yes.
Okay, so 2.5. What do you guys get? Anybody came up with something cool?
780.
7 1780
34,
34
Yeah, 3475.
75 amp. Okay, thank you. You take 34 75 amp, take this one to 240.6, and guess what you're gonna get? What do you guys get? Anybody can guess? I don't think there's anything in between. 4,000 amp. 4,000 amp. So get yourself a 4,000 amp fuse and a 4,000 amp disconnect with it. You know, you have to have the fuse. By the way, fuses, guys, if you look, fuses have to have a disconnect. That's why I showed fuse and a disconnect right with it, because they want you to be able to isolate the system. Fuse cannot be used as an isolation means, you know, by itself. First you disconnect it, and then you go grab it and change it. Unlike circuit breaker, where circuit breakers, you know, you can isolate the system with the circuit breaker. Number 4. The last thing is number 5, guys. And you're going to be asking me, say, Chad, have you lost your mind because of the holidays? Is this a grounded system? And listen to the term carefully. Is this a grounded system? What is a system? First, to answer this question, you have to ask me, what is a system? A system is a transformer. Is this a grounded system? Meaning, am I asking you to say, is this a grounded transformer?
No.
No. Okay, so this is very confusing in the code, guys. Every system has a grounding with it, but not every system is grounded. Not every system is grounded. When they ask you, is this a grounded system, means, is the transformer grounded in either side? Is it? No, it's a delta. It's not grounded. Grounded. What does grounded means? You take one from the gut of the transformer to Mother Earth. Look at all the windings. Am I grounding any of the windings? No. That's an ungrounded system. Ungrounded system. Ungrounded system means the transformer is not grounded. That doesn't mean you don't pull a ground with it. That's the most confusing one. Guys, you say, well, Chad is ungrounded. Well, how come that you're pulling an electrode grounding conductor with it? I'm pulling the electrode grounding conductor because of safety. I'll tell you in a second here. Because of safety, even though the system is ungrounded. So if you go, Brad, and measure the voltage between the ground and phase A, you wouldn't see anything. You can literally grab phase A and tie it directly to the ground and nothing will happen. No short circuit, nothing. That's the beauty of a delta, ungrounded system, guys. They use it in assembly lines and transmission lines because you can get the first hit and you're not down. You can handle the first short circuit on one phase. A second short circuit on a different phase will bring you down. That's why they use the ungrounded system. And say a squirrel is climbing over here on the pole and land on short to ground, nothing will happen. You don't trip and turn the power off on half of the city of Minneapolis because of a squirrel dancing on the transmission line or distribution line. In an assembly line, guys, a guy made a mistake. A guy made a mistake and grabbed a screwdriver right here while you're doing it and shorted. Most of the shorts that we have ground faults there. Most of them, because There's no dumber than rock guy that goes grab phase A and phase B and start bolting them together. I mean, that's, you gotta be really, you're gonna be lost your mind to grab phase A here, bolt it, grab another piece, bolt it, and let it, I mean, that's like that, and you're lost, unless you lost this, and then that's the Lord's issue. But ground faults are very common. You're working on phase A and accidentally you touch the frame here, which is grounded. That's a ground fault, very common. You're changing the ballast and you touch the frame or the conduit. So very common ground faults. So this will handle the first ground fault in any phase, no problem. Continuity of the system continues. The second, on a different phase, not on the same phase, on a different phase, will bring you down. So if C and G are tied together, no problem. If C and B are tied together, that's no problem. If BC goes down to ground, you got yourself a line-to-line short circuit, right? If you bring C to G, tie these two together, and tie these to G, then C and B are tied together. So you have a short circuit between two-phase short circuit together. So that will bring you down. So long story short, big introduction. I need it's an ungrounded system, but I need a grounding electrode conductor for it. Why? Because if I have a first ground fault, no problem. I alarm, the alarm actually, this is an alarm that there's a ground fault on the phase. Why? When you have time, on a weekend, when the assembly line is down and nobody's working, go fix it. But you don't interrupt the process. Process is money, I've been told. And being bred as capitalist as I am, that dear to my heart. That's a joke. It's supposed to be a joke, for Pete's sake here. Okay, then long story short, big introduction for let's size the grounding electrode conductor. The same way, guys. You're going to size it based on the conductors coming out of the transformer. How many sets we had? We had 6 sets times 500 each, right? 500, that will give me 30, 0, 0. Do I have KCM? You take this one to table 2, 50.66, and that will give you no matter what you're going to get. You're going to get 3 aught. One conductor, 3 aught. Now, I am waiting for Spencer to look me in the eye and say, Chad, let's do the main bonding jumper. Size the main bonding jumper. Do we have main bonding jumper? The system is ungrounded. Out the window. No main bonding jumper. Very important. Grounding electrode conductor, no problem. 3 aught, the max that you can go to. You can go higher, but that's as you have to go 3 aught, but you can go higher than that if you want to, but you don't have to. Main bonding jumper out the system. Why? Out the door. Why? Because the system is ungrounded system. So I'm going to write a little note here just to remind you guys. No system. Actually, this would be a main bonding jumper. It could be anything depending on how you use the transformer. In this case, most likely it's going to be main bonding jumper because this is a service coming to my building. If I own the transformer from both sides, the high and the low, it becomes a system bonding jumper. 2 names for the same thing. No main bonding jumper because system ungrounded system. That's what I want to, because ungrounded system. It's a delta. By the way, can I have a YY ungrounded system? No problem. Just don't take the gut of the Y to ground. You can have can I have a single phase ungrounded system? No problem. Don't tie the neutral to ground. I can make this transformer ungrounded system and they use it, guys, for isolation. You take this little guy, this is isolating transformer. If you don't take this little green and tie it to ground, this is an ungrounded system on this side. So to make it grounded, you have to take that green, white and go tie it to the grounding electrode conductor. It becomes grounded. Any transformer can be ungrounded system. Just don't tie it to Mother Earth. Don't tie any of the transformer sides to Mother Earth. The last thing, guys, I want to do, I just want to bring to your attention that this transformer, I don't know if you noticed, Mr. View, we found something that you don't know. We have 10 meg, 6, the impedance 6%. I want to bring to your attention the impedance, 6%. I need to find a short circuit on the secondary side of a transformer. Meaning, if I go short these together, see what I did? Right in here, right at the terminal transformer. You only do that one for testing, which is the worst scenario. That's kind of the doomsday. If you do it this way, you go bond the 3 together under one line. How much current do you expect to go through these conductors? Meaning, are they going to burn or not? So that's what we're going to do. We're going to find short circuit on the secondary of the transformer. To do that, guys, I need you to remember what was the full load amp of the transformer 1390. Okay, so what is it, 7?
Yes.
No, 6, I don't think we have 7. Short circuit current. Short circuit current, guys, very easy. You take I, short circuit, divided by I, secondary, over impedance, which is Z. Z is the impedance. Okay, let's do that. What was it, 1390, Polly?
Yes.
Did you call it Polly or Holly? Polly. Polly 1390. One of our faculties, Polly. 1390 divide, what was Z? 6%. How do you convert a percentage into decimal? 0.06. And what would you guys get? Z is the impedance. Z is the impedance. Anybody come up with the number? Brooke?
23,167.
It's 23.167.2. 23.2, right? In kVA. 23.2 kiloamp. 23.2 kiloamp, right? The approximation to K? Because that's what we thought K language. So approximately 23.2 K. Now this boy that you're looking at here is rated for 50K. 50K, so can handle up to 50,000 amp. This system on the secondary side, you need 22K. So can this fuse, at least short circuit wise, handle my system? Short circuit. Amp wise can't, because it's 65 amp. At least short circuit, it can handle it. So the fuses, guys,
That's the fuse?
that's a fuse, yeah, or similar fuse. So for fuses, guys, there are two sizes. Jesse, here's my fuse on the high voltage side. This is that little niche. No, not up chair. There you go. My fuse. Okay, so for my fuses on the secondary, what was the size, Polly, the secondary fuse size? Actual size, was it 1600 amp? Was the secondary?
4,000.
4,000, the secondary was 4,000 amp. And it's a 4,000 amp fuse, and the interrupting rating is 23.2 kilo amp. So since it's available 23, most likely it's going to be 25 kilo amp. So that's, you're going to go buy yourself a fuse that's 4,000 amp and interrupting rating 25. Why 25? Because it's slightly higher than 23. Where would I get the standard ones? Industry standards. You have to go to books. So that's my fuse. Doesn't look like a fuse, but mind my drafting skills. Mind my drafting skills. Okay, 5 minutes, and I do have an example for you that's really cool about this one is about tabs with transformers. Really cool one. Tabs with transformers. Might as well keep going. This is one of the most common combination that you're going to encounter in the industry. One of the most common. I have, let me just, and please pay attention, this is real installation. I have a main panel, 48277, feeding a transformer, 75 kVA, delta on this the primary, Y in the secondary, and from the secondary side of the transformer, I'm feeding a receptacle panel that's powered at 28120. So I'm taking a voltage level of 48277, dropping it down to 28120 so I can dump it across all these 120 loads. That's what I'm doing. Very common, guys, in commercial industrial when you have 480. Very common transformer. Most of the time, this D, write it down because that's helped you a lot, guys. D is the distance between basically the overcurrent between the overcurrent protection device in this panel and the overcurrent protection device in the second panel. So the distance of the cables, the cable distance. So if my transformer is right here, from the overcurrent protection device you measure the cable goes to the transformer, through the transformer, out of the transformer to the second panel. So that's a distance of the cables through the transformer between the two panels. Through the transformer between the two panels. 25 feet or less. That's rule tab for transformer 25 or less. You're going to find this information just if you think Chad is going to bring it from his basement. 240.5. Okay, 240.21B3. So this is coming, all this info is coming from 240.21B3. Okay, 240.21B23. If you guys go there, you're going to find it. A couple of things. If the distance, the both cable on both sides, if the distance, both cable and both sides, guys, are within 25 feet, and the conductors are protected at an amp, not more than what they're rated for. So if the conductors are 100 amp, you protect them at 100 amp. And if they are protected from physical damage with a conduit. These are, which is typical, guys, typical. Okay? And we need to size, here's what we need to do. We need to size the overcurrent protection device and the conductors for this system. The overcurrent protection device, the conductors for this system. I want to start this time, guys. I would like to start with, since it's a panel, I want to start, guys, by sizing the panel. I want to size my panel. So I'm going to start by sizing number 1 is the panel. Number 2, overcurrent protection device. Number 3, conductor on the secondary side. Everything is on the secondary side. On the primary side, I'm going to do the same thing. Size, or the panel, I'm not going to size the panel on secondary because panel is a big deal. I'm going to size the conductors, number, that would be number 1, 2, 3, 4. And number 5, the overcurrent protection device, number 5. The panel will be sized based on other loads. Based on other loads. Okay. Let's do the same rule. For this particular situation, guys, for this particular situation, let's take, so we need to size the panel, number 1, I'm going to call this as RP panel. RP panel. So find the full load current, IP, I secondary equal 75K divided by 1.73. What's the voltage on the secondary side? 2.8. Everybody knows why the voltage here is 2.8 because it's tied to a 2.8 panel. 2.8. What do you guys come up with? 208. I hope now it's not going to confuse people with 208, 208. We're going to come up with 208. 208 amp. 208 amp. So the transformer can only contribute up to 208 amps based on the design right now. Okay? Remember when we size the panel. So how much panel can the transformer contribute? 208. So let's go find our, this is how I would do it. This is how, again, how I would do it. I would take the 208, grad to where DeWalt. DeWalt, no multiplication by 1.25, no multiplication by anything else. Directly to DeWalt, 3, was it Brad, 3-12? 3-12, 3-12. What do you get? 120, 225? 225. You get 225 amp. 225 amp. So my panel size, actual cover or aluminum size inside this panel is going to be 225 amp. So, and the reason why I bring the cover, Brooks, because an aluminum cover, because that's when you do estimation, and you do estimation, and the project is very expensive, and you need to do so-called engineering design. You go back and you say, well, you know, we went up on this panel, we could go down to make the project affordable for the customer. If you don't know what size panel, actual panel versus overcompression device, you can't do that. So anyway, 225, so that's the panel size. Since I'm on it, I want to go, guys, do number, what did we say, number 2? Number 2, overcompression device. Number 2 is overcurrent protection device. Number 2, overcurrent protection device. Now I will bring to your attention one thing. One thing. I'm going to do it this way, and don't ask me why. Is this number 2, is it the secondary overcurrent protection device? Is it or not? This guy, number 2, could be considered the secondary protection of overcurrent protection device only if it's right next to the transformer. If it's not right next to the transformer, it's not the secondary protection. Why? If I move 10 feet from the transformer and I put my overcurrent protection device, that's not my secondary protection. That's the panel protection. Yes, sir.
So what's the distance limit?
25. See that 25?
No.
Between here,
Yeah, between there.
based on this scenario that I'm going to show you right now, it could be any. Here's how the scenario. I could have 24 feet here. I could have 24 feet here and 1 foot here.
No. My question is, at what point does it stop becoming the secondary overcurrent protection and become the panel? You say right
At
next
point,
to the transformer.
right at the
What's
transformer.
distance?
Right at the transformer. So if your transformer is sitting right here, it will be an enclosure attached to the transformer where it's bust to the fuse. That's a secondary transformer. Right at the secondary of the transformer. I hate to use 0 feet because you might have to do cover inside the enclosure right attached to the transformer to be considered secondary protection of a transformer, which is, you know, right at the transformer, which is really, unless you do utilities do it this way. They have an enclosure for fuses right at the transformer. That's why they have these rules, guys, the tab rules. That's why they have the tab rules. If you follow with me, I'll explain it in a second here. So this is not a secondary transformer protection. What I'm sizing right now, it's not a secondary transformer protection. It's a protection for the panel. Okay, so let's say the overcurrent protection device. This is how I do it. We're going to do the 208. Where's my 208? So I'm going to take the same thing, 208. Let's take the 208. Take the 208 to 240.6. Now, Brad, you're going to tell me, Chad, what happened to the 1.25? That's not a secondary protection of a transformer. Okay?
I wasn't going to ask you that.
Okay. Now, 208, what's the next overcurrent protection device? 225? Did we hit the jackpot here? So 225, 225 amp panel. So my panel happened to be the same size as the overcurrent protection device, which it doesn't have to. Okay? 225. Any question, guys? This is very, very important because you get it all the time. This scenario, 25 between them. Any questions? So I size my overcompression device. I have a 225 amp panel tied to a 75 transformer. We're good to go. We are powering all our receptacle from this panel. The reason, if you wonder, guys, why didn't I multiply by 1.25? And I told you that before, because when I size, I have to size this transformer. I added all my KVA load of the 208 load, everything. I added them up and derived them, and I came up with Brad and Brooke and Ryan and Spencer. I came up with 73 KVA. So what's my next standard? After I multiply by 1.25 for the continuous load and all this stuff, I came up with 73 KVA load transformer that I need. So I go next to where? To the next standard, which is 75. That's why I don't multiply again by 1.25. It's already oversized, basically. The transformer is already oversized. That's how it should be. It's already oversized for the continuous load, you know. Okay, so let's go. What's the third one, guys? The third one is the conductors. Now, since I can size the conductors based on the 208, but since I'm feeding panel, always get into the habit. It's a panel. Always get into the habit of matching the conductors to the overcompression device when you feed a panel. You really don't have to. By code, you can go size the conductor based on 208. It's not a good idea. It's not a design good idea. So I want to say number three, my friends, is secondary conductors, or these are RP feeder. The receptacle panel feeder, right? It's the same conductors. The secondary and the RP feeder. Okay, so I want to size it bit. I want to say match overcurrent protection device. Very good idea. So 225 amp. You're going to take it to 310.16 under 75-degree column. How many conduct? I'm going to pull full neutral. I told you guys anything 400 or less, full neutral. So I'm going to have 4 conductors. Everybody knows why 4? Because it's a Y. And I need full neutral. 4 out. 4 out. I need another one to 4 out. Spencer? 4 out. 4 out. My conductors are 4 out. My conductors are 4 out. Ben, did they
No,
bother you
no,
too much?
no, no.
Number 4, the closer we get to the full time, the more I start losing it here. Number 4, my friends, is we need, what was number 4? DJ. Where's DJ when you need him? Number 4 was the conductor. Number 4 was the conductor. Primary conductors. Primary conductors for the transformer. Primary conductors for the transformer. Okay, then I need I primary equals 75K divided by 1.73. Which voltage? Holly, I'm going to be dividing on the primary side.
40.
Are you Holly?
Yeah.
40.
I think she's taking it.
Speaks for me.
What's the amp? Anybody? Ben, have you done? 90. 90 amp.
Someone took my
90 amp.
maybe I'll get one for Christmas.
90 amp.
Just what I wanted. Lamborghini.
Now, let me bring to your attention one thing. That 90 amp, that continuous load is already incorporated in it. Okay? You can multiply by 1.25. I don't. The continuous load, as I said, when we size the transformer, is already incorporated in it. So, again, only for this scenario when we're dealing with panels. So I'm going to go take my 90 amp directly to 310.16 and I go strictly by amps, guys. A lot of people say, well, if you know that the lugs are rated for 75, Spencer, you can use a 75. I don't know what the transformer lugs are rated for. Most of the time they're rated for 75. I'm going strictly by the amps. The amps will shoot me where? To 60 degree, thank you. 60 degree column, and that will give me how many conductors? 3 conductors, because it's a delta. And 2, number 2? Number 2, thank you, Mr. Bell. Number 2. 3 conductors, number 2. 3 conductors, number 2. Piece of cake, overcam protection device, primary, overcurrent protection device. Now both of them, Spencer, are low voltage. So which column are we going to go to in which table? 450.3 A or B? Both of them are low voltage. So we're going to go to 450.3 B, right? B is the okay. I'm sizing the primary. What's the multiplier for sizing the primary? Do they need me to decide? I'm using a circuit breaker if it matters. I can't remember. On the primary side, I'm using. Okay. What's your option?
We have primary and secondary for this.
I have primary protection only.
So 1.5.
Do I have a secondary protection in that system? I have primary protection only. Primary protection only, right? The secondary was way downstream. Primary protection only. Okay, so what's my multiplier?
1.25.
125. 1.25 times, what's my 90? What would that give you?
113.
113. 113. Doesn't have the number 1 on it? Okay, so you take this one to where? To 240.6 will give me 125. 125. 125 amp. 125 amp. 125 amp. So I size the overcam protection device, guys, to the transformer, out of the transformer to the panel. 125.
That's his question about the taps. How long can they be? It kind of explains it. It explains it pretty good in 240. Was it 240? C.
Okay. Is that how long the tab is?
Well,
So
it
the
says
10 minutes.
transformer secondary conductors where they can be protected by the primary.
Yep.
And there's all kinds of different scenarios.
Yeah.
When they can,
Where they can,
how long they can be and how.
absolutely. C, transformer secondary protection, protected by the primary. Under, yeah. There's so many scenarios, guys.
Yeah.
The scenario that I have is that it's strictly 25 total length. There's a scenario where the 10 foot from, we'll take these scenarios, but let me just concentrate on this scenario, okay? Any question guys about this? Any question about this? Let me draw this one now and show you based on the tab, that I can go do slightly different. So I just want you guys to look at this. I want you to remind me a few things though as I go. I'm gonna draw just a one-line diagram of the system. This is called a one-line diagram. Here's my, okay. This is just one phase of the system. Okay. What was that? This one was 125 amp. Okay. This one was what? 225? 225 amp. This conductor was number 4? Number 2. No, I thought that was what number 2.
Oh,
That was
never mind.
number 2.
I'm on
The secondary was number
secondary. Or primary is number 2. Secondary is
number
4.
number 4 4. Okay. Look at this carefully, guys. And then here's the tab rule. The tab rule, guys, is that start from right the transformer here to the overcome detection device here. From here to here is no more than distance is equal or less 25 feet. You apply these rules only if that's a scenario. Only. Including the transformer, the distance says no more than 25 feet. Okay? No more than 25 feet. No more than 25 feet. Okay. Now, here's what the rule for the tab says. What happens, guys, is sometimes you size it this way and the overcome detection device trips. What would you do? So if you guys look at, this is a scenario that we have. Based on the tab, here's what it tells you. I'm going to call, which color? I'm going to use a color, a blue color. We use blue color, black. I'm going to use black. So this conductor, I'm going to call this one, guys, C. Here's what the tab says. Tab rules based on sizing.
Where did you get to the 24 amps from that?
125 amp.
No,
It's 225, you have to find out.
Mr. Webb, why didn't you tell me that? 225 amp. That was really small, sir. 25 amp. Okay. So rule number one, guys, for the tab, really interesting. Conductor must be equal or more to 1/3 of overcurrent protection device primary. Overcurrent protection device primary. That's rule number one. The conductors must be, the amp of the conductor must be more or equal to 1/3 of the overcurrent protection device. And we'll try it right now. This is, I'm going to call this is C1. C2, which is a conductor right here. C2. C2, conductor number 2, guys. The same rule. This must be equal or more than 1/3 of the overcurrent protection device for P, for the primary, except you have to take the primary to the secondary voltage ratio. The primary to the secondary voltage ratio, which is in my case, V primary over V secondary. You have to take the V primary over V secondary. Now we're starting to probably lose some of you. These are the rules for the tab rules. The conductor, if you are to stay within, the conductor amp cannot be, it has to be equal or less than half of the overcome protection device. Let's test what we did, guys. Let's test what we did. Let's just do a test on what we've done. Okay? What's the conductor amp? What's C1 amp? What's the amp of number 2 under 60-degree column? What was the amp of number 2? Number 2 under 60-degree column. What's the amp of number 2? You guys come up? 95. So 95 amp, more or less than 1/3. What's the overcome protection device? 125 of 125. Can anybody do the math for me? 125. Forty-two amps. So it has to be equal 95 amps. Is this true? Is 95 amps that we size for more or equal to 42? Yes. If it's not, then you have to up your conductor. So we checked rule number 1. The second rule. Let's do the second rule. What's the amp for 4/0 under 75, guys? The amp for 4/0 under 75. The amp for 4/0 under 75. The amp for 4/0 under 75. How much?
230.
230. Here's a 230 amp. Must be equal or less than. What's the primary voltage? 480. What's the secondary voltage? 208. Times 1/3 times 125. Okay, do the math.
So that's 1.25.
No, 125, Mr. Graf.
Oh, 1.25. Okay, that's
Yep.
it down.
Okay, so 230 amp more or less than. Can you guys do the math on that one? 96. Okay, 96. Is this right? Is this right? 96. Yeah. I mean, is it right, the formula that we have here? So the two. That's right. Why these are important, guys? Why these are important? So I met the tab rules, no problem. These are the rules, Mr. Spencer. The amp for the conductor, based on the tab, must be more or equal than 1/3 of the overcomputation device. Now, why this is important, guys? Why this is important? Let me just show you one little thing why it's important. The amp of the conductor was, you guys told me 95 here, the primary, 95, times 95 by 3, Brad. 95 by 3,
285.
285. 285, go down on the conductor, the overcomputation device. What's the 285? 250? Down. 250. I could have easily, based on the tab rules, put 250 amp right in here. No problem. Based on the tab. If I stay within that 25 feet. Why it's important? Because if you put 125 and every time you energize your transformer, you trip because of error in the transformer. The tab rules solve this problem for you. Just based on the conductor size that you did. Based on strictly on 95. 95, if you read this the opposite way, this says the overcomputation device cannot be more than 3 times the conductor. Okay, here's the conductor 95, 3 times is 280 some. You go down to 250. So this I can right now change the 125 to 250, nothing would happen. That's the power of the tab rules. Okay, so I want to say if I'm doing the tab right now, if this is giving me a hard time starting, I can go change this one directly to 250. And we know why 250. 250 came from 3 times 95. 95. Can I bug you to give me the answer again, Brad?
285.
285 amp, and then you go down to 250. All right, so that's on the primary side. Let's go on the secondary side and then we're done, I promise you. On the secondary side and then we're done. On the secondary side, okay, this is kind of really funny on the secondary side. It would tell you the conductor, how are we going to transfer that one? Cannot be, when you take it 3 times, so it's going to be 3 times, what did we say? We're going to size the conductor. We start with the amps, which is 230. We're going to multiply the amps by 3, but we're going to divide it by 48028. So here's the math on that one. So the overcurrent protection device could have been 3 times the ampacity. What's the ampacity of the conductor? 230, right? You guys gave me that one. Times, now remember, I'm going to flip the voltages. It becomes 208 over 480. So that's how high I could have gone on the primary to protect the secondary. On the primary to protect secondary. Can you guys do the math on that? $299. 299 amp, and then you're going to go down to where? Because it's not standard, down to 250. 250. 250 amp. So the same, surprise, surprise, came up with the same answer, 250. So I could have, had I come with 200 here, by the way, had I come 200 here, then 200 rules. Then that overconduction device cannot be more than 200. Long story short, guys, this will give you a way of oversizing your secondary because of inrush and still meet the code. Still meet the code. Yes, there is no secondary protection for the transformer whatsoever here. But if I maintain this 25 feet, I have no problem going as high as 250 on the primary side, and the conductors stay the same size and still meet the code. If I maintain that 25 feet. If I go 30 feet, then I'm stuck with what I designed. 125 right now, and all stuff, you're stuck with what you designed. Between 125 and all this cable. And triggers. Huh?
You'd be stuck with it much more.
Yep. FYI, guys, in 2011, right now, the NEC code said that you have to have a disconnect right next to the transformer or identified if it's farther away. So this circuit breaker right here, most likely is going to be very close to the transformer right now, within sight. They say within sight though. Or it has to be locked in the open position if it's not within sight and identified at the transformer. Any question, guys? This is one rule of the transformer rules. There's a few other rules I'll be going over as we go through. I'm sorry it's monkeying around with numbers, but it is. It allows you to design different than what my code said in his book. You know what I mean? Based on the tabs. Based on the tabs. And just 1 second here. All these stuff that I did, guys, is 240.21. What did we say? 240.21. I thought I gave you that. 240.21 B3. If you don't believe me, go to that particular scenario, read it. It will tell you exactly what these. I changed it into formulas just to make it more, I think, more mathematically inclined. Any question, my friend?
For the 299.
I'm sorry, Mr. Bev.
You see the code 240.
299.
No, in order to go down, what's the code there?
Oh, what's the code? If you read, this is the code.
Oh,
If you read this, it tells you the overcome protection device cannot be more than, and they don't tell you anything about what if you don't hit a standard, what would you do? They didn't say anything about it. It tells you cannot be more than this. So, well, more than 299, I can't find a 299 fuse, and they're not allowing me to go up by directing me to go up. If you read this, there's no direction to go up, so I have to go down. Any question, guys? Spencer, I'm sorry, the tab rules are funny and huffy, and the tab rules are really, they can save you a lot of money if you understand them. A lot of engineers don't even look at them. They just oversize things and call it a day. You know what I mean? You just don't want to go mess around and monkey around and you oversize and call it a day. But they really can save you money if you understand them well. Especially that one with that transformer. This is every industrial building is going to have this scenario. Every building is going to have this scenario. Every guaranteed. Because you have 480, 277, and you need 120 to power your receptacle. So how are you going to get to 120? You got to have a transformer that's 480 to 208. I did not multiply by 1.25. That's my method, guys. If you want to go multiply and you end up with a bigger panel size, but you know the transformer would never be able to supply you with these amps. You know, it's not designed to. I guess you can overheat it a little bit if you want to. if you multiply by 1.25, guys, you end up with oversizing things. A lot of things will end up oversized. Any question, my friends? Ben? Mr. Bew? We're missing a few here. That's all what I have for you guys today. And that's probably the last time we're going to hear Chad talk about calculation. We're going to switch after the holidays to lighting calculation. But when it comes to the spring, we're going to deal with a lot of other stuff like this. So make sure you guys hang around for lunch. Go grab something to eat before you leave.